So in today's video, I'm going to be walking you guys through an example of a linear programming application problem. So first of all, let's just read over the introduction to the problem. It says, you own Funky Furniture, a store that makes tables and chairs out of Lego pieces to sell. A chair is made of 1 large and 2 small pieces. A table is made of 2 large and 2 small pieces. Currently, you have 8 small Lego pieces and 6 large ones. If the profit for a table is $16 and for a chair is $10, then how many tables and chairs should you make to maximize profit for your Funky Furniture business? Okay, so this problem has a lot of information in it, and sometimes when there's so much going on, we can organize the information in a table, and that's what we're going to do below. So the idea here is we're going to let x equal the number of chairs. So we see how we have that little x right there. And y equal the total number of tables. Okay? So when we're writing our constraints, we need to think about what is the total number of large and small pieces that we have to work with. And we see in the problem we have 8 small and 6 large. So our constraints in this problem are we can't go over the 8 small. So I'm going to put that as our total number of small pieces, or our 6 large pieces. So now if you think about it, how many large pieces do I use when I make X chairs? Well, it says a chair is made with 1 large piece. So that means that for X number of chairs, I have 1 large piece per chair. So that's 1X. And then it says I have 2 small pieces. So that means for every chair, I have 2 small pieces. So I'm going to write 2x. Doing the same thing for tables with the y variable, a table is made of 2 large, so I'll have 2 times the total number of tables, and 2 small, so I'll have 2 times y as well there. Finally, I'm going to fill in the profit. So it says that I should make a profit of $16 for every table. So that means I do 16 times the total number of tables. And $10 for a chair. So that means I should do 10 times the total number of chairs. Now that I've organized this information, it's going to be a lot easier to write the constraints. So here's the table all filled in. So as you can see, if you take a look at the constraints below, they come directly out of the table. So if you go straight across in the large pieces column, we see the 2x and the 1x and the 2y. We want to add those together, and all together that needs to be less than or equal to the total number of of large pieces we have to work with, which is 6. And that's where the equation x plus 2y the inequality x plus 2y is less than or equal to 6 comes from. If we move on to the second row, we see for small pieces I should have 2x plus 2y, and that has to be less than or equal to 8, which is the total number of small pieces that I have, and that's where this second constraint comes from. Now, the reason we have these last 2 constraints of x is greater than or equal to 0 and y is greater than or equal to 0 is because we cannot have a negative number of tables and chairs. It doesn't make sense to have a negative. We could have 0 chairs or 0 tables, but we cannot have a negative value here. Because what would it mean to have a negative value for a number of tables or a number of chairs? Okay, so now I'm going to as quickly as possible, graph our system of inequalities or our constraints. So first of all, I can quickly put on the line x is greater than or equal to 0. That's going to be a vertical line. Oh, and I'll just mention I'm going to draw in my axes just in the bottom left corner. So this will be the y and this will be the x. So now when I go to draw in the inequality x is greater than or equal to 0, I'm basically just tracing along the y-axis. And y is greater than or equal to 0, I'm tracing along the y-axis. Okay, so I know those are kind of our lower bounds for our feasible region. Now I'm going to graph x plus 2y is greater than or equal to 6. So I'm quickly going to think about the y-intercept. So that means where x is 0. So if I plug in 0 for x, I get 2y is equal to 6. So y is equal to 3. So I'm going to plot that point. That's the y-intercept. To get the x-intercept, I'm going to plug in 0 for y. So I would do x plus 2 times 0 is equal to 6. And then I see I get x equal to 6. So if I count over 6 on my x-axis, and I should get a point right here. Okay. So now to connect, I can just draw a line through those 2 points. And if I think about which way I want to shade, if I plug in 0, 0 into that inequality, I get 0 is less than or equal to 6. So I do know I want to shade below, but I'm going to save my shading until after I graph the last line. So for the final inequality, 2x plus 2y is less than or equal to 8. That gives me an x-intercept of 4 and a y-intercept of 4. So coming back to my graph, I count up to 4 on the y and 4 on the x. And then I can connect those 2 lines. And try to make that a little bit straighter. Okay, so if I think about shading for this inequality, if I plug in 0, 0 for x and y, I get 0 is less than or equal to 8. So I also want to shade below. And then it becomes kind of obvious to me where the feasible region would be. So it kind of is within this little strange shape right here. So now I want to identify my vertices, because I know that if I'm trying to maximize my profit, it's going to appear at one of my vertices. So if I take a look, my first vertice is the origin, so I'm going to call A 0, 0. Then I'll come up to that point right there, call that B. That is the point 0, 3. Where those 2 lines intersect is the point 2, 2. And lastly, so I'm calling C 2, 2. Lastly, I'll have D, B, 4, 0. Now that I've identified my vertices, I'm going to be able to plug into my objective function to maximize the profit. So just rewriting our vertices, we had 0, 0. We had 0, 3, 2, 2, and 4, 0. And the objective function is this 10x plus 16y should be equal to our total profit, because we cost $10 per chair and $16 per table. So I'm trying to maximize P equals 10x plus 16y. So plugging in at each vertice, I can try to find where is my profit going to be at its maximum. So at point A, I'm plugging in 0 for x and y. And this should be a pretty quick one. We should just get 0 here, right? If we don't make any tables and we don't make any chairs, then we're going to have zero profit. For point B, that's the 0.03. So I'm doing 10 times 0 plus 16 times 3, which gives me a profit of 16 times 3 is 48. So it would be $48. Next up is point C, 2. So I get profit is equal to 10 times 2 plus 16 times 2, which is 20 plus 32, or 52. Finally, to do point D, kind of running out of space, I'm just going to do it right below. So point D, the profit would be 10 times 4 plus 16 times 0, which is 40 plus 0, which is just 40. So now, if we take a look at our 4 different values for the profit function, it becomes clear that at vertex C, I have the maximum profit. So the point that's going to give us the maximum profit is point C. Now, what does this mean in the context of the problem? Well, it means that when we produce 2 chairs and 2 tables, and I'm getting those 2's from that ordered pair 2, 2, we will have the maximum profit of $52. So we're going to be practicing doing an application problem in class. So hopefully this will kind of make more sense as you begin to apply this.